Well, we have oil now, right? So just to kind of reiterate how we got here, we talked about zooplankton and algae and other things dying, producing kerogens, those kerogens converting to alkanes, right? If you guys remember our hydrocarbon chains, and that stuff rising up through the surface, bubbling out. The Chinese are getting after it with bamboo poles. We talked about the Drake well, and all of the ways that we recover oil. So at that point, again, we'll simplify here, but basically the oil goes into a truck or a pipeline, oftentimes a pipeline, because it's actually much easier to do it that way, and send it off to something called a refinery. And we have actually a network of pipelines. You can see here large areas where we do a lot of refining. They have a lot of pipelines that actually bring the oil directly from all over the place, actually, to those refining centers, particularly Houston. Off the top of my head, I know that I think Billings, Montana, there's a lot of refining that happens up there. So moving oil by pipeline is pretty reasonable. Pipelines are often, obviously in the news. Everyone remembers the Keystone XL pipeline. It was one particular example, but the reality is moving oil by pipeline is the status quo. Right? That's what we do. The other option is to either put it in a truck or put it in a train car, right? So you can see oil cars on a train. Trains crash, trucks crash, but pipelines can occasionally leak, right? So when we think about something like, should we be moving oil through a pipeline? When we think about an oil spill, it's really easy to focus on, and there have been cases where oil pipelines have spilled or leaked. But it's clearly the most secure way to transport oil. So there have been notable train wrecks and car accidents, where there's a big spill associated with that. But we move most oil by pipeline. So what happens next? Right? It gets to a place called an oil refinery. And it's important for us to remember at this point that crude oil is all kinds of stuff. So remember our alkane chart? You can see here all of the different hydrocarbons, from short molecules all the way up to long molecules, and even some more complicated ones that are not shown on this list. Well, crude oil is a mixture of all of that stuff. And to make crude oil really useful, we have to separate out all of those different fractions of the oil. And that involves what we call fractional distillation. So distillation, you might think whiskey, right? At least that's what I think of, right? Some moonshiner out in the forest with a still. I guess you probably wouldn't set up in the forest these days, but yeah. So what they're doing in the case of alcohol distillation is you have a big vat that's got some sort of mash in it, which is a mixture of mostly water but a little bit of alcohol. One of the characteristics of alcohol is that it has a boiling temperature that's lower than water. So if you heat that fluid up to 160, 170 degrees, the alcohol is boiling off as steam, and it's being concentrated and drips out as pure alcohol, and the water stays behind, right? So you're distilling, in that case, the alcohol fraction. Alcohol is lighter molecule than water, which means it has a lower vaporization temperature. So to get out of the alcohol world, we're going to take basically that same principle and apply it to crude oil. And rather than, in the case of an alcohol still, where you collect the steam essentially that comes off of the top, we use a fractionation column. And what that is basically a tall vertical column, and the fluid is brought in at the bottom and heated at the bottom, and that means as you go higher up in the column, it's cooler at the top. So there's a temperature gradient, and that is what's going to allow us to separate out all of these distillate fractions. Somebody go ahead and draw a diagram here. We'll also look at a few, but I'm going to draw a diagram so we can kind of talk through it. So this has got to be the simplest oil refinery ever, but we just want to understand the basic concepts here. So we've got our crude oil. I mentioned, oftentimes it's actually piped in. Very rarely is it trucked in, but brought in by train, brought in by oil pipeline, or, in this case, a truck, just to make it simple. And remember that crude oil is this black sludge, right? It's a mixture of all kinds of different things, and it's not very useful on its own. We're going to try to make it useful here. So the first thing that we do is the oil kind of comes out of the oil refinery, and I've drawn this little box here. This little box represents a furnace or a heater. So at this furnace, the oil is actually heated, generally through what we call a heat exchanger. We're going to learn more about heat exchangers later. They're much more important in other aspects of like power generation. So at this point, we have oil that comes into the bottom of our fractionation column. That's what this thing would be called. So oil that comes into the bottom of our fractionation column comes in at about 350 to 400 degrees Celsius. Hot, hot, hot. And just like we saw with our, when we thought about making whiskey in the backwoods, right? In that case, remember the alcohol boiled at a lower temperature, and so it would rise up as steam earlier. So if we think back to what's in our crude oil, and again, think about all of these alkanes, right? So long, different lengths of chains. So each of those molecules has a different molecular weight, and because of that, each of them has a different vaporization temperature. So the stuff comes in pretty hot, and what happens is that's basically it goes to steam, and that steam rises up through that vapor rises up through the fractionation column. And when a group of molecules get to a temperature at which they're happy, they're going to condense and they're going to turn back to a fluid, right? So that's the part of the still where we take the steam and condense it right back into a fluid. So as this steam or this vapor is rising up through, it crosses different temperatures. So this is in Celsius. Generally, it ranges from about 350 or 400 degrees Celsius at the bottom to really low temperatures, so roughly 20 degrees Celsius up at the top. That's like 75 degrees Fahrenheit. That's room temperature. And then notice I've drawn these little kind of funky things. What those are called are bubble caps. And the way they work is pretty interesting. So if we think about, so here if we were to imagine a vapor rising up through this fluid, or rising up through this column, it's forced through the inside of this cap, and then that vapor is actually forced out through its own condensate. So at each different temperature, we have these different steps. And what happens is molecules that are shorter or longer, remember, have different temperatures at which they'll turn into a vapor or turn into a fluid, right, if we're going the other way. And so at these different temperatures, different lengths of alkanes separate or fractionate, right? That's what we call it, a fractionation column. So here, again, I've kind of drawn just a little bit of a close-up view of how these bubble caps work. So the fluid would come up, and it would get caught on that level of the fractionation column, and then there's actually a collection spout, right? So we separate that oil into many different fractions, and those fractions contain molecules of different weights. So the heaviest weight alkanes here, still heavier but not the heaviest, kind of medium range, light alkanes, and then the absolute lightest. And it turns out you're going to recognize some of that stuff. This is when crude oil starts to become really useful. So up here in the top, this is the lightest stuff, right? This is the stuff that's coming out, again, kind of close to room temperature. Methane and butane, two fuels that you've probably thought of and you think about as gases, right? Those are actually gases at room temperature, whereas some of these other things don't have a vapor pressure low enough to be a gas at room temperature. So if we move down one bump, so still fairly light, petrol, right? Gasoline. this is the stuff that we use for our cars. And remember, we talked about octane as being the alkane that was really important to us, right? It's what we use for gasoline. But remember, in that case, octane was 8 carbons. So methane is 1 carbon, butane has, I think, 4? I'll have to double check. But these are short chain alkanes. Petrol, we're starting to get longer. So bumping down, longer chain alkanes. Kerosene, bumping down even further. Diesel fuel, continuing on our trek here. Fuel oil, this is the type of fuel that we use for things like ships, right? They use really kind of sludgy oil. And then the heaviest stuff off the bottom, so we see asphalt, wax, lubricating oil, right? That's all the super long chain alkane, the sludgy, the heaviest of the stuff. And so now this is all separated out into really useful things. It's worth pointing out that I've dramatically simplified this, but I think that's always the case in a class like this. One of the things that I left out is there's also a fraction in here that's called naphtha, which is a group of alkanes. It comes off in the gasoline kerosene range. And naphtha is the fraction that we actually use to make plastics and other chemicals, right? So all of the different things that we make from oil essentially are represented by different fractions here. So you can see here's an image. Hopefully you're able to see this clearly. In this case, we have many different fractions, right? So not just the simple ones that I drew on the board. And you can also see that it even gets more complicated on the back end. Some of the stuff is kind of further processed. But you can see, ship oil in the bottom, petrol up in the kind of close to the top range, plastics and some other uses. And then also methane and butane, which are coming out the top. So that's how we make it useful, right? We take this sludgy oil, which is a mixture of all different sorts of molecules, we heat it up in a furnace, and then we let the vapor essentially separate out at these different temperatures. And so that's what allows us to separate that crude oil based on the groups of molecules that are in there, right? So again, those all have different uses. All right, so now we're going to talk about a couple of examples of unconventional oil. So not just the standard story that we've told. And then we'll wrap it up for the week, but still a couple of videos left. All right.